welcome to lecture 27. So in the last class we have seen how to do or how to solve the circuit if the excitation is sinusoidal and if I'm interested only for steady state response. So then I don't want to write the differential equation, I just want to solve or I just want to analyze the circuit using or I just want to analyze the circuit for steady state response. Then how can I do? So instead of writing the differential equations, there is an approach called Phasor approach by which you can find out the sinusoidal or the steady state response for the sinusoidal excitation. Okay, this approach was quite simple. Then also we have seen the different power calculations in the AC circuits, right? Like your active power, what is active power, reactive power, apparent power, and complex power. Also we did the power audit. Okay, now in this class, from this class, we will start with our total new topic that is called the magnetically coupled circuit, or I will say the coupled coils. Okay, so we'll start from here onwards, that is magnetically coupled coils. Okay, so before starting it, let us see something that till now what we did, we have analyzed the circuit for the resistive network, inductive and capacitive network. Okay, now this is especially new element, or rather not new, but it is the not the inductor, basically it is the coupled inductors. When coupled inductors, then how can we analyze the circuit, that basically we have to say in this particular lecture. Okay, so in order to say, let us start with, according to the Faraday's law of induction, what it states that if you have two coils, okay, and if two coils with turns N1 and N2, and if they place near each other and two currents flow in both of the coils, for example, let me draw it better. So if I have two coils like this, okay, and if they are placed near each other with the number of turns N1 and N2, and the currents flows in it, like let's say I1 and I2, and the two currents flowing that we have already shown, and also voltages are V1, let's say these are the polarities V1 and say V2, then what will happen? Then these two coils affect each other. It means whenever there is a coil or closed loop in a magnetic field, and say magnetic field is varying, then what will happen? Then voltage would be induced in the coil, right? So naturally, when the two coils are brought to each other, and if current flows in both the coil, then the flux of one coil will link to the other coil. Okay, it means that when the flux of one coil link to the other, it means that they are mutual, right? Means they are mutual means what? They share the common magnetic flux, and then this flux change with time. So if it will happen that the flux will change with time, then there will be the EMF induced in it, and this kind of phenomena basically is called the transformer, right? As we know it, called as transformer. So what next? This is my two coils having N1 and N turns, and say self inductances are L1 and L2, for example. So according to Faraday's law of induction, a current I1 is flowing in a coil L1, right, may induce or may produce a current I2 in coil 2 in a closed path containing a second coil L2. So the sufficient condition for introducing the current I2 in coil 2 are, there are two conditions basically in order to produce the current I2 in coil 2, is that the part of flux, say the part of flux is say phi1, so part of flux phi1 in coil L1 in coil L1 must, or you can say the part of flux in coil 1 must be magnetically coupled to coil L2. This would be the first condition. And second shot, flux phi must be time varying. Flux should not be constant. If it is a constant, then it's of no use to induce the voltage, and it not satisfy the loss. Okay, so this phenomena of the two coupled coil basically known as transformer, and we know it consists of two winding, primary and secondary. If something has been energized, then that kind of winding is basically called as primary winding, and if both the coils are energized, then I can say that both are the primary Both are the primary coils or primary side of it. Okay, so basically transformer is what? Transformer is a physical device, okay, and it can transform or change one level of either voltage or current or impedance into other level of voltage, current or impedance respectively, may be higher or may be lower. So also if currents are changing in both the coils, then EMF will be induced in each other, and this phenomena described by the parameter called basically mutual inductance between two coils. Understood? So if currents are changing both the coils, then EMF will be induced in each other, and this will be represented by, this phenomena will be represented by the parameter called as the mutual inductance. Okay, so how to represent this is by mutual inductance. Okay, which will be able to say that how much coil L1 has been magnetically coupled with coil L2. Okay, so in order to relate the mutual inductance with their self inductances, we know that M will be equal to K, geometric mean of the voltages of self inductances of two coils, that is M is equal to K into L1 L2. This is the relation where L1 and L2 are your self inductances, whereas your M is the mutual self inductance. L1 or L2 are the self inductances, okay, and M is the mutual inductance, and K is called as coefficient of coupling. Okay, so now let us again to specify that K has to be greater than 0 and it has to be less than 1. Now with this condition, what if K is equal to 0 and K is equal to 1? So for example, if I am saying if value of K is equal to 0, so what does it mean? M will be is equal to 0, means what? There is no coupling between two coils. So when K is 0, for example, I have two coils and they are not coupled with each other. That is, one coil is here and say other coil I put it something, let's say 1 kilometer far away from it. So obviously there will be no coupling between these two coils, right? So means what? The flux of one coil is not at all going to be linked with the flux of other coil, right? Means what? Their magnetic fields are very weak. That's why they are not at all coupled. So this will happen when there is no relation, or when this M is equal to K, geometric mean of product of self inductances will not satisfy. Okay. The next is what is extreme case? Second extreme case is K is equal to 1. So if K is equal to 1 means what? Both the coils are perfectly coupled. So whatever the flux produced in coil L1 will be magnetically coupled with coil L2, right? So practically it is not at all possible, means it is not usual, as some of the flux leaks out to other magnetic substances, right? So generally the value of K basically has to be less than 1. Okay, nonetheless, so if what I was saying, if K is equal to 1 means what? Your transformer will be called as the perfect transformer. Means what? If the coils are perfectly coupled with each other, then that condition then that kind of the device I can name it as perfect transformer, right? So means that no flux leak out, and all the flux from coil 1 will be linked with coil L2. So now there is one more word called ideal transformer. So what is the difference then? How can we define, or how can we differentiate the perfect transformer and ideal transformer? So for this, in perfect transform, what will happen? As we said, coefficient of coupling is 100% 1, but in ideal transformer also K is equal to 1, and one more condition, that your self inductances L1 and L2 are very large, means what? They tends to infinite. So what will happen? Very negligible amount of, that is phi is equal to Li. So if L is large, what will happen? Your very negligible amount of current required to produce the flux. Okay, so this is the condition basically for the ideal transformer. Okay, fine. Now, so yeah, so now with this introduction, let us define what is the meaning of self inductance and the definition of mutual inductance basically. Okay, so to define the self inductance and mutual inductance, let me draw first the magnetic circuit. So suppose I have this magnetic circuit. Let's say this is my magnetic core. Okay, suppose this is my magnetic core, and to this I have wound the wire like this. So this become coil with some certain amount of turns, say for example N1, and to this say I will energize this coil, and suppose I1 current, let's say time varying current, is flowing into this coil. Okay, like this and this. Okay, now if this current is flowing, what will happen? If this will flow, then we can use the Fleming's right hand thumb rule. What is our right hand thumb rule? That if I'll like this, if whatever the core is there, I'll consider that core this way, right hand thumb rule. So my fingers will be like, suppose core is kept like this. So what will happen? Thumb is in opposite direction. So the thumb direction will indicate the direction of flux which will be produced by flowing the current in coil L1 or in current in coil 1 with number of turns n, right? So this flux will produce, and what is that flux? Let me call the flux will be produced at phi t1. This is my total flux. Okay, now out of this total flux, what will happen? Some or very fraction of flux will leak like this, so it will try to complete a path this way by its own, and one more flux, this is, let me name this is my leakage flux phi L1, and let me say this is my some flux which most of the flux almost the flux is flowing in the magnetic core. Okay, like this in this particular direction, and direction has been calculated by the right hand thumb rule. Okay, so this way I calculated, or this way we can decide the direction of this flux, and this flux we can call it as a mutual flux. Okay, phi m1, and this flux is my leakage flux when current I1 is flowing in coil 1. Okay, so what can I say? Your total flux will be in terms of two things, that is phi m1 mutual flux and your leakage flux. Okay, so remember when there will be the magnetically coupled coils, there are two terms, that is self inductance and mutual inductance, that we are going to define it. Okay, so this way is that. Okay, now this we define as mutual flux. Let me write it also. This is your mutual flux and this is the leakage flux. Okay, now for that, if I would like to calculate what is the self inductance of coil 1, so self inductance or L has been defined as phi I over L or the amount of current, that is 1 ampere current flowing. It means what? It is the leakage, sorry, not phi I, but it is self inductance will be total linkage over the 1 ampere current flowing. Okay, so in coil 1, if I would like to define the self inductance, what it will be the total flux linkage. So how much it will be? N1 as a number of turns into total flux, that is phi T1, and when suppose this I1, okay, let me write capital I1, doesn't, suppose this I1 that is 1 ampere current is flowing in it, per 1 ampere current flowing in it, right? That will be my self inductance. Okay, so let us divide this into 2, that is phi Tm, we know it is mutual flux plus leakage flux over I1. So this also I can write as N1 phi M1 over I1 plus say N1 phi L1 over I1, not right. So this is the leakage flux. Note that this leakage flux is very, as I told, it is a very small amount of fraction, like maybe 2% or 3% like this. Okay, so with this now, let me define the two inductances. We can have the two terms in self-inductance. One, this I will define as LM1, that is called magnetizing inductance, and this will be your leakage inductance. So self-inductance again can be divided into two, that will be your magnetizing inductance, and this will be my leakage inductance. Okay, fine. So now self-inductance is divided into two, that is magnetizing inductance and leakage inductance. Magnetizing inductance will be contributed by the mutual flux phi m1, where leakage inductance will be contributed by the leakage flux, which will try to complete its own path in coil L1 only, or in coil 1 only. Okay, so again we say that okay, leakage magnetizing inductance will be very greater than that of the leakage inductance. Okay, now with this let me draw the shortcut representation instead of drawing the magnetic circuit and all. So this, suppose if I draw the coil like this, where I1 current was flowing and say polarities are this. So what will happen? As we know, inductor will store the magnetic energy, so it is equivalent to the energy source, which will be this way. Okay, and the value will be L1 di1 by dt. Okay, and polarity suppose like this, plus minus. So it will be L di1 by dt, EMF will be induced in it. Okay, so this is the equivalent. You can draw this way, or this is the equivalent in terms of the source, as the inductor source the energy. Now let me draw again the the magnetic circuit, where suppose now only, let me draw here. So instead of, what I can say, now suppose this is my coil, okay, L2 coil, to this current is passing, say I2. So what will happen? Again, right hand thumb rule, flux will produce in this direction. Okay, so this is my total flux, which will be again phi m2 into leakage flux. This way, again this flux will move in this magnetic core that way. Okay, fine. Now this way we can define the self inductance for coil 1. Similarly for coil 2 also we can define. Now let us define the word called mutual inductance. So in order to define it, let me draw the magnetic circuit again. Where is that? Fine. Okay, this is my magnetic core. To this I have wound the wire like this. Suppose like this. Okay, this is my coil 1, where I1 amount of current is flowing. Now suppose this is my coil 2. This way. Okay, this is my coil 1, this is my coil 2, and suppose that coil 1 carries current I1, coil 2, let's say it carries no current carry. Fine, and then what will happen? By carrying I1 current in this basically coil, what will happen? Due to the right hand thumb rule, flux will produced, and the direction of flux will be in, means the flux will be like this. This is mutual flux and this is leakage flux. This is my mutual flux phi m1, let me name it. And what will happen? This flux will link to coil 2. Okay, so that linkage means what? That is your mutual flux linkage. Okay, so it has been linked to coil 2. So now I want to find out how much mutual flux linked to coil 2 is defined as M21. It is the amount of the mutual flux has been linked to coil 2, and M21 I can say that can be defined as the mutual flux linked with what? With coil 2 by current I1 in coil 1, by or due to flow of current, due to flow of current I flow of current in coil 1, and that I can name as I1. Okay, so now let me define what is my M21. To do this, to find out how much mutual flux has been linked with coil 2, that is M21 is the mutual flux linked with coil 2 due to the flow of current in coil 1, that can be again defined as the flux linkage, where it will flux linkage with coil 2 divided by the current, which current is I1, and this can be written as N2 is the flux is the number of turns in coil 2 into which flux, the flux produced by coil 1 because of the flow of current in coil 1, that is I1. Okay, now what is my aim? My aim is to compute what is the strength, how much is the strength of mutual flux. So this can be computed as the magnetic flux density for coil 1 into the cross section area of, let's say, linear magnetic field, and we know magnetic field density can be defined as the constant of proportionality that depends on the medium mu 0 mu r into the magnetic field strength. Okay, and how can you define that? It will be mu 0 mu r, and magnetic field strength will be defined as Ni by L, means N1 number of turns in coil 1 into current divided by the length of or average length of mutual flux. Okay, I can say that. So if I substitute everything in phi m1, then what I can write? Mu 0 into mu r into n1 I1 divided by L into A. And just for my convenience, this also can be written as N1 into I1 divided by L over mu 0 mu r into mu 0 mu r, mu 0 mu r into A. Okay, and this quantity is called as the reluctance. Okay. So with this, my M21, that is the mutual flux linked with coil 2 due to the flow of current in coil 1, is what is it? N2 phi M1 by amount of current is flowing per amount of current flowing. So this is N2 over I1 into phi 1 is N1 I1 over L upon mu 0 mu r A. Okay, and basically N1 and I1 will vanished from this term, so M21 will be now equal to N1 into N2 upon reluctance. Okay, this is the amount of flux which has been linked to coil 2 due to the flow of current in coil 1. This is M2. Now what I'll do, now I'll take it the same magnetic core, but now I will not supply current in coil 1, but I'll energize the coil 2 and let me see what will happen for in that situation in terms of the mutual inductance. Okay. So suppose this is the magnetic core. Okay, let me define that, and there I have wound the wire like this. Okay, similarly at this in on this side something like this. Okay, now what I'll do, I'll carry the I2 current in this particular coil 1. Say this is N2, these are N1 turns. Okay, and this carry no current. Okay, so now what will happen if I2 current is carrying in this case? So if this current is carrying in this coil 2, what will happen? By the right hand thumb rule, there will be the flux produced, and what will be that flux produced will be this direction. Okay, so this will be, now there will be again the two types of fluxes. This will be your leakage flux and this will be your mutual flux, which let me call it as phi m2 in this particular direction. Okay, and this also I can write as phi t2, total flux will be phi m2 plus phi L2. This is your leakage flux and this is your mutual flux. Okay, and again same way I can define the self inductance L2 equal to total flux linkage, which will be number of turns N2 into phi T2 upon the current is flowing, which will be again N2 phi T2 we know, which will be mutual flux plus leakage flux divided by I2. This I will separate out, N2 phi M2 over I2 plus N2 phi L1 over I2. Okay, and this is what? This is your what is it? This is your magnetizing inductance and this is your leakage inductance L2. Similarly, what we defined for coil 1, the same way we can define for coil 2. Now let us calculate or let us think on the mutual inductance. So in this what will happen? Let us see the diagram. Now this mutual flux will flow like this, and what will happen? This will link to this coil. Now I would like to know how much by how much amount the linkage has been done. So this amount is nothing but your phi m2. Okay, this much I have to calculate, and for that I have to define the term that called mutual inductance, which will be defined this way, that is M12, which is nothing but the mutual inductance in coil 1 due to the flow of current in coil 2. Okay, and this can be defined as the flux linkage in coil 1. So how much is flux linkage? N1 into the flux, how much flux linkage, that is the phi m2 over the current flowing in coil 1, that is I1. Okay, now what next? I would like to find out how much phi m2, how much it has been linked. So in order to know the phi m2, how will it be? I should know how much is magnetic field density into your cross section area of the linear magnetic circuit, and then bm2 also, that is magnetic density, we can express as mu 0 mu r into the magnetic strength of coil 2 into the cross section area, and we know how much is hm2, that is mu 0 mu r into the field strength is, and this will be how much? N2 I2 over the average length of the mutual flux into A, and this I can write as N2 I2, like what we have written previously, L upon mu 0 mu r into A. Okay, and this again I can write as N2 I2 over reluctance R. So with this this much magnitude, that is phi m2, this much amount, the flux linkage is N2 into I2 our reluctance. Okay, now let us put in our M12, which is the magnetic mutual inductance of coil 1 due to the flow of current in coil 2 is what was it, N1 upon I1. No, this is due to the flow of current, that is I2. I'm sorry, just made a change. M12 will be due to the flow of current in coil 2, I2. Okay, so this is basically my I2 into phi M2 will be N2 I2 upon reluctance, and this I2 will get it cancelled again. This will vanish. So what remains now, it will be N1 into N2 upon A. Oh, let me write, this is N1. Let me write properly, N1 N2 upon A, which will be M12. Okay, and look at the previous magnetic circuit which we have taken for M21. M21 is also N1 N2 upon R, and M12 is also N1 N2 upon R. So with this, what I can conclude from it, that M12 which was equal to M21, which is the product of the terms of coil N1 N2 and upon reluctance, okay, and which is equal to mutual inductance M, right? Okay, so this way you can define the mutual inductance, and generally how to represent. This is my coil, this is my second coil. They are linked, and this linkage can be represented with the mutual inductance M. Fine. So what we have done, we have discussed, we have discussed that magnetic core and having two coils with turns N1 and N2, so that what we will have, M12 will be equal to M21, which is equal to M, that is the mutual inductance. Okay, and what was the self inductance? It was L1 was 5T1 N1 upon I1, and L2 was 5T2 N2 upon I2. 5 to 1 again you can write as the mutual flux plus leakage flux, and that L1 can be write as the magnetizing flux plus the leakage flux. Similarly for coil L2, magnetizing flux plus leakage flux. Okay, and again to note that LM1 will be very greater than leakage flux. Here also LM2 magnetizing inductance, sorry, here magnetizing inductance. Okay, this is magnetizing inductance, and this is your leakage inductance. So this is magnetizing inductance is very greater than leakage inductance. So it will be very small amount of, or it will be very fraction. Fraction means let's say 2% or 3% of it total. Okay, so this way you can define the self inductance and mutual inductance. So with this we stop here. In the next class we will see the dot conventions. How can we make it? How can we identify the polarities by the use of dot convention? And how can we write the equations for series and parallel coupled coils? Okay, so we stop here. Thank you.